February 1, 2009, 2:10 a.m. Atlantic Ocean. At 35,000 feet, an Airbus A330 slices through the darkness above the Atlantic. The cockpit lights are dimmed. Outside, nothing but black. The moon's behind them, swallowed by clouds. Inside, two pilots scan their instruments while 216 souls sleep in the cabin behind them. The autopilot hums along. Everything's normal. Match 0.82. Smooth sailing. Then, without warning, the autopilot disconnects. A cascade of warnings floods the cockpit. The aircraft lurches right. The airspeed indicators plummet from 275 knots to 60, an impossible reading. The altitude drops 300 feet in seconds on the display, even though they're not descending. The first officer grabs the side stick and instinctively pulls back, hard. In 4 minutes and 20 seconds, this aircraft will fall 38,000 feet into the Atlantic Ocean. That's about the same time it takes to toast a slice of bread. How does a state-of-the-art fly-by-wire Airbus, one of the safest aircraft ever built, end up in a catastrophic stall at cruise altitude? What split-second decisions sealed the fate of everyone aboard? And why didn't any of the three experienced pilots recognize what was happening until it was far too late? This is another story about warning signs ignored for years, about systems that failed when they were needed most, and about how quickly everything can go wrong when you're flying through the night over the middle of the ocean. I'm Captain Peter Mercer, and what you're about to hear is this story from a pilot's point of view. Welcome aboard. Let me take you back to May 28, 2009, Rio de Janeiro, Brazil. The crew operating Air France Flight 447 had just arrived from Paris for a scheduled 3-day layover. We know very little about how they spent those days in Rio, but here's what matters. The first officer, who would soon be flying this airplane, had brought his wife along for the trip. That tells us something, my friend. It's unlikely he spent the entire day before the flight resting, and there were indications this might have been true for the other pilots as well. Flight 447 was scheduled to depart at 8 p.m. Rio time, that's 11 p.m. Paris time, which meant the crew would be operating through the entire night with a planned arrival in Paris around noon on June 1st. They'd be flying straight through what we call the window of circadian low, that brutal period when it's hardest for the human body and mind to stay alert. Because of this, and because the flight would last 12 hours and 45 minutes, an extra pilot was added to the crew to allow for scheduled rest breaks during the return flight. That meant 3 pilots would be flying together, 1 captain and 2 first officers. The captain was 58 years old with 11,000 total flight hours, 1,700 of those as pilot in command on the Airbus A330. Experienced, competent, by all accounts a solid aviator. The first officer was 32, the least experienced of the 3, with 3,000 flight hours and 800 on this aircraft type. He'd earned his A330 and A340 type rating in 2008, just the year before this flight. The third pilot, I'll call him the relief pilot, was a 37-year-old first officer with 6,500 total hours. But here's the thing. He was actually the most experienced on this specific aircraft type, with 4,500 hours flown on the A330. He hadn't flown much in the 3 months leading up to this flight because he also worked as a management pilot for Air France. Before the flight, the pilots reviewed all the standard documents: weather, flight plans, NOTAMs. The weather looked good for departure in Rio and arrival in Paris, but the en route weather? That seemed a little more complicated. The flight would cross the equator, and with it, an area over the Atlantic known as the Intertropical Convergence Zone, the ITCZ. In this zone, easterly trade winds from the northern and southern hemispheres converge and can force humid air from the sea surface upward. This creates powerful thunderstorms that can reach up to 60,000 feet, much higher than most aircraft can fly, which means any aircraft flying through this zone could be subjected to flying between and sometimes even through parts of these storm clouds. Now here's where it gets tricky. Storms that form over water in the ITCZ sometimes contain less water than storms that form over land, which makes them harder to see on the aircraft's weather radar. So pilots have to be very careful navigating around them because they can still be pretty severe. It's likely the pilots discussed the risk of encountering these storms and carried extra fuel to navigate around them if necessary. They warned the 9 flight attendants about possible turbulence and its impact on the cabin service. Before we move on, we need to talk about the types of precipitation you can encounter in these thunderstorms. Most people are familiar with heavy rain and sometimes hail that comes out of these clouds. But as you look higher up through the clouds, things get a little more complicated. Because of the very strong updrafts inside the cloud, water droplets can be forced upward into extremely cold air and become supercooled. This means they're still in liquid form, but as soon as they hit any surface, they'll freeze instantly and create clear ice. Sometimes supercooled droplets collide with snowflakes, forming soft ice crystals. They're not as hard as hail, but they're large enough to be heard when they hit the aircraft. This type of precipitation doesn't form heavy ice on the aircraft structure like supercooled rain does, but its significant volume can quickly clog and overwhelm sensors and probes on the aircraft, especially pitot probes. Let me explain what those are real quick. Pilots require precise measurement of airflow over the wings, since this determines the aircraft's performance. To do this, they use a type of probe known as a pitot tube or pitot probe. These probes are often located along the front of the aircraft below the cockpit and look a bit like gun barrels. They have a hole in the front where air enters, and then the total pressure is measured inside the tube. The Airbus A330 has automatic electric heating, but to accurately measure airspeed, static pressure must also be measured so it can be deducted from the total pressure of the pitot probes. This static pressure is measured from a different device called a static port, and that static pressure is used both to calculate airspeed and, crucially, the aircraft's altitude. These various pressures are sent to the aircraft's computers known as air data modules, or ADMs. The ADMs calculate the correct true airspeed, but another factor that'll become crucial in this story is that the static pressure from the static port must be corrected depending on how fast the aircraft is flying. This occurs because the air flowing over the aircraft surfaces around the static port creates localized pressure differences based on speed. These corrections are made automatically by the ADM computers. Because of the criticality of airspeed and altitude, the aircraft has 3 independent sets of probes and computers. Now here's what matters. More than 9 different occurrences of this type of obstruction had been reported on Air France flights during 2008 and 2009, and these reports, along with how to recognize and deal with the problems, had been published in safety bulletins distributed to all Air France pilots during the year, prior to the accident flight. Airbus had started investigating the problem and discovered that a new type of pitot probe was more effective at preventing these issues. They issued a bulletin suggesting an upgrade to these probes. Air France had started upgrading its first Airbus A330s about a month before Flight 447's departure, and the accident aircraft was scheduled to have its probes changed after arrival in Paris. But why was changing these pre-approved probes only a suggested action? Why wasn't it mandatory? Because the temporary loss of airspeed due to this problem was very rare, only lasted a maximum of a couple of minutes, and there was a defined procedure that pilots should follow if it occurred. At Air France, this procedure was known as unreliable airspeed. Since this problem had been reported multiple times, it was incorporated into recurrent training for all Air France crews during 2008 and 2009. The training included unreliable airspeed exercises, but only at low altitude. That's because it was considered more critical for safety due to proximity to terrain, but also because the aircraft's performance was much better than it would be at high altitude. Unreliable airspeed can be very difficult to diagnose because the failure will look different depending on what caused it and how severe it is. During the exercises Air France crews practiced, the autopilot didn't disconnect, and there was no warning sounding in the cockpit when the failure occurred. The unreliable airspeed procedure now included the use of memory items, that is, critical safety items that pilots should perform immediately from memory. But their use was optional depending on the situation, and that was interpreted as necessary only if the aircraft was close to the ground. Notably, none of the Flight 447 pilots had received recent training on how to handle a stall approach and recovery, particularly at high altitude. The last stall training they'd received was during their type rating on the Airbus A320, which they'd all done years before. And that initial training they'd done was at low altitude, where a lot of emphasis was placed on using power to recover the aircraft and pull it out of the stall with minimum altitude loss. Reducing the pitch angle was a secondary action. Now this idea that the engines will have enough power to pull an aircraft out of an extremely high angle of attack is also going to become very important. After the 216 passengers boarded and the crew was ready, the pilots requested pushback and began backing away from their gate at 22:29 UTC, just 9 minutes behind schedule. The captain and his 2 first officers were in the cockpit as they headed to the runway. At 22:29, the aircraft began rolling down the runway in Rio de Janeiro and performed a completely normal takeoff. They climbed along their clearance, which took them on a northeasterly course following Brazil's coastline. After passing 20,000 feet, the relief pilot left the cockpit to begin his scheduled rest period of approximately 3 hours. He returned to the crew rest area with 2 bunks behind the cockpit. We don't know exactly when he left because the voice recordings begin after midnight UTC. In any case, the 2 remaining pilots received clearance to climb to their initial cruise altitude of 35,000 feet. Once established in cruise, they were talking with controllers in Brasilia, then switched to Recife control. Recife control would be the last to have radar contact with the flight, because in that control area, they were still flying largely over land. But once they passed into the next FIAR region over the Atlantic, they'd move away from radar coverage and instead be following oceanic traffic separation procedures. Now, flights over oceanic areas require special training procedures and aircraft equipment. Due to the curvature of the Earth, aircraft are equipped with HF radios to allow long-range high-frequency communication. These radios use layers in the ionosphere to bounce signals and can therefore reach much greater distances. When the aircraft passed the area navigation waypoint called INTOL, the pilots contacted Atlantic Control on one of the 2 HF frequencies they'd been given. Then the pilots attempted to log into a new system being tested at the time in the area called ADSC. This system would use automatic reports sent by satellite from the aircraft to update its position to air traffic control, showing where it was even without radar coverage. Another interesting thing this new system could do was send an immediate report if an aircraft deviated from its assigned course or altitude. But unfortunately, due to a formatting error in the flight plan that had been filed, the pilots couldn't log into this new system. And so, as soon as the aircraft left conventional radar coverage, it could no longer be tracked accurately, something that would have serious consequences. The Airbus A330 is a fly-by-wire aircraft where the pilot's movements on the side stick and rudders are electronically interpreted by a computer and sent to hydraulic actuators for execution. This type of control comes with many benefits. For example, it makes the aircraft substantially lighter, but mainly, it allows the aircraft to monitor certain safety parameters and ensure those parameters aren't exceeded. Parameters like excessive roll and pitch angles are monitored, as well as protection of maximum and minimum speeds, and a host of other parameters too. Now, detractors of the system say this allows the aircraft to have the final word over the pilots, but that's not entirely true. Only maneuvers that are truly extreme and ultimately dangerous are blocked by the system. But the fly-by-wire system requires that the pilots operating it truly understand how it works and when those protections actually function, and when they don't. This is obviously true for all aircraft, but it's especially true here. And why is that? Well, for these protections to work properly, the computers monitoring them need to be absolutely certain they're using the correct parameters to begin with. If they're not, the computers will back off and remove those protections because they're really not sure what's happening. These computers receive inputs from various sources: pitot probes, static ports, inertial reference units, angle of attack vanes, among others. They combine all this data in 3 air data reference units to form together the ADIRS. As long as all 3, or at least 2 of these ADIRs agree with each other, the aircraft control computers are happy and can continue operating in what's called normal law. Normal law means all protections are available, and it's basically impossible for the aircraft to stall or enter an out-of-control situation. But if 2 or more ADIRs start sending strange information, a couple of things will quickly happen. These inconsistencies could affect the automatic flight system, like the autopilot that controls the aircraft, the auto throttle that governs the engines, and the flight directors that guide the pilots. It's logical if you think about it. The aircraft won't attempt to navigate or control itself if it's not sure what's happening. It'll let the pilots figure it out, and following that same logic, the aircraft control computers will degrade from normal law to alternate law 1 or alternate law 2, depending on the severity of the problems. The difference between normal law and alternate law 2, which will soon be relevant on this flight, is that the protections the aircraft normally has regarding maximum angle of attack or stall protection will no longer be available. This will be shown by the removal of warning indicators like the barber pole on the primary flight display, as well as yellow crosses where limitations would normally be displayed. The other difference is that the aircraft's roll control changes. In normal and alternate 1 laws, roll inputs on the side stick command a specific roll rate of the aircraft. If the pilot inputs a specific roll rate, the aircraft will provide it and compensate for disturbances from gusts. It'll be very stable and straightforward to use. But in alternate law 2, the side stick gives direct commands to the ailerons and spoilers instead of commanding a specific roll rate. This means there are no roll protections or stability control. This also increases the aircraft's sensitivity to roll, particularly at higher altitudes, where there's less aerodynamic damping due to thinner air. Another key difference between a conventional aircraft and an Airbus with fly-by-wire is the pitch trim system. In a conventional manual flight aircraft, the yoke directly controls the flight controls, and pilots must make trim adjustments manually. In an Airbus, the side stick requests from the control computers a horizontal turn rate and a vertical pitch or G-load. When the pilot establishes a specific pitch, the elevators will initiate the pitch, and the huge horizontal stabilizer will automatically move to continue maintaining that pitch without any input from the pilot. This also means there's no great tactile feedback from the stick. If the aircraft is entering a strange trim position due to low speed, as would be the case in another aircraft, the 737 I'm flying, in normal law, that's not a problem, because the aircraft also protects against approaching an angle of attack high enough to make it stall. But that's not the case in alternate law. Now, these differences are really important for any pilot to know. But crucially, even more, they need to understand them and need to be able to retrieve this knowledge when things start to go wrong. As Flight 447 continued along its route, they received a message from their company warning them about reported storm activity ahead. The first officer adjusted the scale on his navigation display and mentioned some build-ups visible ahead. Then the pilots began discussing possible ways to avoid the turbulence these clouds would bring, and the first officer indicated he was quite concerned about the storm clouds he now saw approaching. At 0146, the first officer dimmed the cockpit lights to see better outside and confirmed the aircraft was now entering a cloud layer. It was completely dark outside with the moon situated behind them, and light turbulence began to shake the aircraft. The crew debated whether they could climb even higher, as they seemed to be grazing the tops of the clouds at flight level 350. But when the first officer checked the maximum altitude they could climb to, it indicated flight level 370. And both decided it wouldn't be a good idea to stay at maximum altitude if the turbulence worsened. Now would be a good time to discuss another topic that'll soon be important. As an aircraft climbs, the outside air becomes thinner. And because of that, depending on the aircraft's weight as well as outside temperature and some other factors, the aircraft will be limited from continuing to climb because the engines simply won't be able to produce enough excess thrust to do so. This also means the engines don't have much excess thrust to deal with any anomaly up there. And because of that, we pilots need to be very careful and pretty conservative with how we operate the aircraft. The only way an aircraft can climb higher than its indicated maximum altitude would be by trading kinetic energy, its speed, for potential energy altitude. But doing so would dramatically increase the angle of attack. At higher altitude, the critical angle of attack at which the aircraft stalls is lower due to the aerodynamic effects of flying near the speed of sound. In short, at higher altitudes, the aircraft will stall earlier and have less thrust available. It'll also be more sensitive and difficult to fly manually due to less aerodynamic damping from the air. After the aircraft entered the clouds, the captain began commenting on the appearance of St. Elmo's fire. This is a clear indication of an electrical charge forming near an aircraft, an additional sign they were approaching thunderstorm clouds. At that moment, the captain pressed a button on the overhead panel that activated the chime in the crew cabin behind the cockpit. This was the signal for the relief pilot that it was time for him to return to the cockpit and take over from the captain, so he could go back to the cabin and rest a bit. The first officer knocked on the cockpit wall to confirm he heard the chime. Air France's standard operating procedures at that time indicated that the first officer in the right seat, who was the pilot flying, would assume the role of pilot in command when the captain went to rest, unless something different was agreed upon. And that's precisely what occurred in this situation. When the relief pilot arrived in the cockpit at 01:59, the captain left his seat and listened to the information the first officer gave the relief pilot. This information included the anticipated turbulence they were currently flying in the cloud and that they couldn't climb higher at that moment. The captain didn't leave clear instructions to the two first officers about how to handle the upcoming thunderstorms. Instead, he left the cockpit to begin his rest. Now we can only speculate why he didn't give clearer instructions. As I mentioned, all three pilots were accustomed to this weather and had flown this route often. So it's likely he found the two first officers more than capable of dealing with it. When the captain left, according to Air France procedures, the more experienced relief pilot assumed the role of pilot monitoring in the left seat, and the first officer continued as pilot flying and in command of the controls. The two pilots discussed the weather conditions they were facing, and the first officer mentioned the intertropical convergence zone. But at this stage, there was no discussion about trying to avoid the cells by changing course. On the other hand, the relief pilot asked the first officer if he'd managed to rest, to which he responded that he'd only slept a little. Later, the relief pilot asked the first officer if he was okay. This discussion suggests both pilots might have been somewhat tired at that moment. The captain had also made similar comments before. The relief pilot also left his pilot seat in the rear position and didn't move it forward to the flying position when he sat down. That probably would have given him a more relaxed position, where he could put his feet up, but it wouldn't be ideal if he suddenly needed to fly the aircraft, which he soon would have to do. At 02:06:05, the first officer contacted the cabin crew to inform them they'd probably encounter some light turbulence soon, and to tell them to be careful. About 4 minutes had passed since the captain left the cockpit. In another 4, the emergency sequence would begin. The first officer began closely examining his navigation display and adjusted his weather radar gain to maximum. This made the weather radar more sensitive and highlighted the weather ahead. Then he asked the first officer if maybe he wanted to go a little to the left, indicating some discomfort with what he was seeing in front of them. The first officer asked what he was referring to, and he pointed to the image on the screen, asking again if they could turn left. The first officer nodded and turned the heading selector about 12 degrees to the left. This was a small correction given the weather they were facing, but it meant they were now deviating from their planned flight route, and they didn't attempt to communicate this change to air traffic control. At 02:08, the cockpit voice recorder detected a change in background noise. This noise sounded like rain hitting the cockpit. Simultaneously, the first officer noticed the temperature increase and asked if the relief pilot had modified the air conditioning. Then he asked, "What's that smell?" The relief pilot recognized the smell as ozone and calmed his colleague, explaining what it was. The passengers' comments and the sound of rain outside indicated the type of weather the aircraft was going through. The change in temperature and humidity in the cockpit probably indicated that large amounts of water or ice were suddenly sucked into the engines, partially overwhelming the air conditioning. 20 seconds later, the background noise intensified, sounding like ice crystals hitting the cockpit. The turbulence worsened, and the first officer reduced speed from Mach 082 to 0.80, the turbulence penetration speed. This reduced the autothrottle power to 84%. Up to that moment, the aircraft had been functioning smoothly, and the pilots were relaxed, supervising the autopilot. We don't know for certain what caused it, but it's very likely that the ice crystals now hitting the aircraft from outside began to overwhelm the heating elements of the pitot probes that provided crucial information to the 3 air data modules. At 02:10, the autopilot and automatic thrust control suddenly disconnected with the corresponding alarm in the cockpit. Simultaneously, an intense gust of wind caused the aircraft to roll abruptly to the right. The first officer shouted, "I have control," and reached for his side stick. This sudden onset of warnings and anomalous aircraft behavior would have probably startled and confused the pilots almost immediately. But at this point, the aircraft was still flying pretty level. only initiating the right turn. As the aircraft continued turning right, the indicated airspeed on the captain's primary flight display and on the standby indicator dropped abruptly from 275 to 60 knots, an obviously erroneous indication. We don't know what the first officer's instruments indicated since they weren't recorded on the flight data recorder, but they probably also descended a similar amount. Remember what I told you about how the altimeter system compensated pressure for higher Mach numbers? Well, because the speed was now indicated as much lower, the altimeter system recalculated its altitude and suddenly showed a drop of 300 feet, as well as negative vertical speed. The first officer, who'd been suddenly thrown into manually flying the aircraft, now reacted instinctively, giving left aileron and raising the nose to correct his altitude. This was the beginning of the sequence of events that would ultimately doom this flight. Because the three ADIRs were showing unreliable data, the aircraft went into alternate law, losing the protections for angle of attack, overspeed, and roll. As I mentioned, roll control became twice as sensitive, which means the first officer had to concentrate to get the aircraft to stop rolling and return to level flight. He began to overcorrect, and the movements he made with the side sticks caused more oscillations, going from right to left and back. It's very possible that most of the first officer's attention was directed to this part of the handling at this point. But remember, he'd also started to raise the nose. The pitch angle was increasing, resulting in a very high rate of climb. When the autopilot disconnected and the warnings began, a brief stall warning was heard in the cockpit. When the warning sounded, the relief pilot asked, "What's that?" Probably due to the brevity of the warning, but it could also indicate confusion about its meaning. The flight directors weren't disconnected by the crew according to the unreliable airspeed procedure, but the command bars disappeared anyway due to lack of reliable data. 11 seconds later, the pitch angle reached 11 degrees up, and the first officer was making maximum left and right side stick input, overcorrecting. He also said, "We don't have a good display," probably referring to the lack of speed information. The relief pilot, in charge of ECAM warnings and the abnormal checklist, shouted that they'd lost the speeds and alternate law protection. Then he continued reading the ECAM messages, but in a way that was difficult to understand and very rushed. Here it would have been absolutely crucial to point out that the aircraft was clearly an alternate law, which means it would handle differently and certain protections were lost. He mentioned that auto thrust had been lost, and the first officer responded by asking, "Engine lever?" showing some confusion about what he was saying. As the auto throttle had disconnected during the failure, thrust entered a mode called engine thrust lock, which meant it maintained its previously selected value of 84%. ECAM instructed the crew to move the thrust lever manually and resume control, but the first officer pressed the auto throttle disconnect button and left the lever in the climb detent. Because of that, thrust began increasing toward climb thrust. Everything mentioned so far happened in the first 18 seconds of the emergency. 10 different ECAM messages appeared, each causing a chime in the cockpit. In addition, the master warning and caution lights were on in front of the pilots, along with a constant chord chime, signaling that the aircraft had left its authorized altitude. This would have been a very confusing and stressful environment for the pilots, and the fact that unreliable airspeed wasn't indicated on ECAM was something the pilots needed to discover for themselves. That might have been the reason they didn't begin executing that procedure at that moment. At 0210, the aircraft's pitch attitude reached 12 degrees nose up. The aircraft was now climbing at a staggering rate of 6,900 feet per minute, more than 7 times higher than the normal rate would be. By passing 36,000 feet, maintaining such a high rate meant the aircraft was trading speed for altitude rapidly. Suddenly, the flight director bars reappeared in front of the first officer, but now they were engaged in vertical speed mode, since they activated in the middle of a climb instead of the altitude hold modes they were in before. This meant the flight directors now showed the pilots the pitch angle required to maintain their current climb of 6,000 feet per minute. That definitely wouldn't have been helpful in this situation, when it's likely the first officer was becoming increasingly overloaded by noise and workload, and it was precisely because of this that the unreliable airspeed memory items included turning off the flight directors. The relief pilot now looked away from the ECAM display, which he'd stopped reading anyway, and reached to turn on wing anti-ice. And that's when he noticed the high pitch angle the aircraft was maintaining. He exclaimed, "What's your speed?" possibly referring to vertical speed, since the speed indication still hadn't returned. The first officer responded, Okay, I'm going down," and began pitching forward, but not enough. This only reduced the rate of climb, but the aircraft continued climbing. The relief pilot continued shouting that he needed to stabilize, descend, and according to 3, it's climbing. So go back down. To which the first officer responded, Okay. The angle now reduced momentarily to about 10 degrees, which still gave a rate of climb of approximately 4,000 feet per minute. They exceeded their calculated maximum altitude of 37,000 feet. Between 02:10:36, the flight directors disappeared again, but the airspeed reappeared on the left, showing the correct speed of 223 knots. This indicated that up to that moment, the aircraft had lost close to 50 knots of airspeed pressure and continued decreasing. The flight directors reappeared briefly twice, commanding a climb of approximately 10,000 feet per minute, which is what the aircraft was doing at that instant. At 02:10:47, the first officer inexplicably reduced power to around 85%. And this is probably a sign of his growing loss of situational awareness and disorientation. The relief pilot pressed the call button to try to get the captain back to the cockpit. He pressed it several times, asking, "Where is he?" He also leaned over and changed the air data selector and the attitude heading selector to the first officer's 3. These switches are designed to change the data input for the displays and weren't included in any checklist. He probably changed these in an attempt to restore the instrument he felt was missing for the first officer. 3 seconds later, the stall warning activated in the cockpit and sounded continuously for the next 45 seconds. The fact that this warning now sounded continuously wasn't verbalized or even discussed by any of the pilots. Instead, the first officer reacted by pulling the controls back, increasing the pitch attitude to 16 degrees nose up, similar to what you'd have on takeoff. The nose-up command also moved the rear stabilizer to its maximum nose-up position, making a possible recovery even more difficult. The aircraft's energy was insufficient to maintain the required rate of climb. Instead, it began to level off slowly, rocking from side to side, which the first officer desperately tried to counteract with the side stick. They were now rapidly approaching a fully developed stall. Now, a stall occurs when the aircraft's wing has exceeded its critical angle of attack, which means it effectively stops being able to create lift, and instead, the aircraft will start to fall. A stall can happen at any altitude. The only thing that determines when it occurs is the angle of attack. An angle of attack is the angle between the wing's chord line and the incoming airflow. Both pilots received initial training on how to handle a stall approach and recovery during their type ratings years ago, but they would never have experienced the sensation of a full stall in the real aircraft. The lack of a visual stall indication or stick shaker on the Airbus, and only an audio warning, could explain why the warning wasn't reacted to, since under stress, one of the first things that disappears in humans is their hearing. At 02:10:57, the aircraft reached its stall angle of attack and a strong buffet began to shake the aircraft. This type of buffet is at a much higher frequency than turbulence and feels very different. The first officer now added full toga thrust, but at this altitude, above the aircraft's maximum performance altitude, the engines couldn't produce enough thrust to maintain speed, much less accelerate. The relief pilot shouted that if possible, avoid touching the side sticks, demonstrating he understood the complications of flying under alternate law. But this was ignored as the first officer continued making maximum inputs on both sides. The relief pilot also said, "Is he coming or not?" referring to the captain. The first officer shouted, "I'm in toga," indicating he'd added thrust, thinking it would be enough to solve the situation. The aircraft still climbed a couple hundred feet more until it reached its maximum recorded altitude of 37,924 feet, and then began falling toward the sea below. You might wonder why the relief pilot didn't take control. He was asking for corrections that weren't happening. Well, we'll never know the answer, but it's probably because all this happened pretty fast. Getting to this point took only about a minute. Plus, the lack of connection between the Airbus side sticks made it difficult for him to see and feel his colleagues' actions, complicating monitoring what he was really doing. At 02:11, the heating elements removed the last piece of ice inside the pitot tubes, and the standby and left speed indicators started working again. The indicated speed was 183 knots, which means they'd lost about 90 knots of airspeed. The aircraft now entered an increasingly rapid descent with the stall warning sounding continuously. The relief pilot shouted, "Oh, we have the engines! What's happening? Do you understand what's going on?" But got no response. The aircraft began rolling to the right, which caused the first officer to continuously give left lateral control, but with very little effect. The first officer maintained his nose-up command with his side stick, continuing this action for the next 40 seconds. Now, for all those who can't believe how it was possible for the first officer to react this way, there are a few things worth considering. The first is that the human brain doesn't function well under stress, and we tend to fall back on our training when that happens. And that brings me to my second point, which is how the Airbus works when flown in normal law. See, the best climb performance you can get from the aircraft is achieved by applying continuous back pressure and toga thrust. That's used during a wind shear or terrain escape maneuver. Since the aircraft won't allow it to stall, it'll just pitch to stay near its maximum angle of attack while using maximum thrust, giving the best possible performance. But that only works in normal law. If you apply that logic, the actions of the overstressed first officer become perhaps a bit more understandable. At 02:11:32, the first officer announced he no longer had any control over the aircraft. The relief pilot responded by saying, "Controls to the left," and pressed the takeover control button to take control, but never verbalized that takeover. Then he made 2 brief left inputs on his controls before the first officer retook command and continued with his own back and left inputs, unsuccessfully. At this point, the aircraft's rate of descent had increased to around 10,000 feet per minute, and the angle of attack was close to 40 degrees, which means it was now more falling than flying. Because it was maintaining such an incredibly high angle of attack, the air now hit the aircraft from below at an angle of 40 to 60 degrees. This would have caused a very peculiar wind noise in the cockpit, but also the angle at which the air hit the pitot tubes and static plates was now so extreme that the pressure became almost equal in both. This meant the speed indication disappeared once again, since the computer interpreted those conditions as completely impossible and unreliable. So the reason the crew found themselves once again without a valid speed indication had nothing to do with ice. From this point on, it was only due to the extreme situation of the aircraft. When the speed dropped below 60 knots, the onboard computers told the stall warning system to ignore the external angle of attack vanes, since such speed could only occur on the ground. This stopped the stall warning in the cockpit, and when the calculated speed dropped below 30 knots, speed flags replaced the speed indication on the pilot's display. At this point, the first officer also said something that gives a bit of insight into why he was acting the way he was. He expressed that he believed they had speed. It's not clear what he based this feeling on, but it could be just his senses, along with the increase in wind noise from outside, and possibly the buffet he was feeling. In any case, the silencing of the stall warning coincided with the captain's return to the cockpit at 02:11:42. That was approximately a minute and a half after the autopilot disconnected and less than a minute after they called him back. He encountered a completely surreal scene. There was no stall warning at this point for the reason explained, but the aircraft was descending with incredible vertical speed, just passing 35,000 feet, the same altitude maintained when he left the cockpit. The pitch attitude varied between 15 degrees nose up and 9 degrees nose down, with 10 ECAM warnings, master warning lights, and strong buffet shaking the aircraft. The captain asked, "What are you doing?" To which the relief pilot responded desperately, "What's happening? Well, I don't know what's happening." The first officer and relief pilot intervened, reporting they were losing all control of the aircraft. "We don't understand anything, despite trying everything." The first officer now reduced the engines to minimum, and given their position below the wings, this, and some actual pitch-down commands, finally caused the aircraft to pitch down to about 11 degrees below the horizon. The first officer said he had a problem. "It's that I don't have vertical speed. I don't have any more displays." The relief pilot mentioned they didn't have valid indications. The vertical speed indication might have been completely down or missing, since the computer considered any value above 20,000 feet per minute invalid. but by finally pitching down, speed began to increase and the angle of attack to decrease slightly. But in a cruel twist of fate, because speed now began to increase, the stall warning system again noticed it had valid indications and began to sound, giving the perverse effect of indicating a stall when the nose was pitching down, but disappearing again when it pitched up. This must have been extremely confusing for the pilots, but completely in line with the aircraft's system design at that time, because it was never thought that any aircraft would even approach that type of situation they now found themselves in. The first officer said, "I have the impression we have crazy speed. What do you think?" Then he leaned over and deployed the speed brake, but his colleagues immediately told him to retract it. This indicates the first officer believed the aircraft was going too fast, not realizing the total loss of speed they were really in. As the pilots tried to solve the problem, the aircraft descended between 10,000 to 15,000 feet per minute, with the nose oscillating between 8 degrees down and 15 degrees up. Each time it pitched down, the stall warning activated, and when pitching up, it silenced. The roll angle oscillated between 20 and 40 degrees to the right, and it was probably the yaw damper controlling the rudder that prevented the aircraft from spinning. At 02:12:10, thrust was moved back to the climb detent, and 20 seconds later the aircraft stopped rolling right, and instead began oscillating from left to right, which the first officer continued trying to correct with his side stick. The relief pilot asked the captain, "What do you think? What do we need to do?" But the captain, who hadn't been informed about the nature of the initial failure or about the rapid climb at the beginning of the emergency, was completely perplexed. He only responded, "There. I don't know. There it's descending." Evidently, he was just trying to understand what he saw on the different instruments. In the following seconds, there were many confused calls from the three pilots. The first officer, still in command, asked things like, "Am I descending now?" The relief pilot responded, "Descend." And the captain, "You're not climbing there," probably referring to his pitch attitude, not what the aircraft was really doing. At some point, the first officer moves the side stick fully forward for a few seconds. This causes a pitch down and speed begins to increase. With that, the stall warning returned, and the first officer confirmed the engines were in toga. This signals once again that this is his standard response to the stall alert. Then he asked, "What do we have in alti?" referring to the altimeter that marked about 21,000 feet. Now this is a bit strange since he should be seeing his altitude in front of him, but unfortunately we can't be sure if the first officer had any valid instruments in front of him since the flight data recorder didn't capture it. Subsequent reviews of the different failure modes in the computers seemed to indicate he did. The captain murmured, "It's impossible," showing he still couldn't decipher what was happening. In the following seconds, the pilots continued debating the aircraft's position and how to level the wings. The confusion is obvious and painful to hear. The first officer mentioned he's at the limit with roll controls, and the captain suggested using left rudder to stop the right bank. This helped for a moment as the aircraft rolled slightly left, but soon continued rolling right. The aircraft dropped below 10,000 feet, and the relief pilot exclaimed, "We're getting there, we're making it." Passing level 100. At that moment, the pilot could hardly have done anything to save the aircraft. The relief pilot shouted, "Wait, I have control," and then began making left inputs. But the first officer never released his control, so the dual input warning was heard several times in the next seconds. The first officer shouted, "Why do we keep descending?" And as he said this, the relief pilot instructed the captain to try rebooting the flight control computers, which he did. But the captain also said it wouldn't make any difference. Then the relief pilot shouted, "Climb! Climb! Climb!" To which the first officer responded, "But I've had the nose full up for a while." That last comment made the captain understand what was happening, and he shouted, "No, no, 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 don't climb!" The relief pilot said, "Then descend," and pushed his stick forward. But the first officer was still holding his stick back, causing a new dual input warning. And since the two inputs now averaged out, nothing happened. The relief pilot shouted, "So give me control. The controls to me, the controls to me." The first officer said, "Go ahead, you have control. We're still in toga." The nose descended 7 degrees below the horizon, and the speed indication returned with another stall warning. 7 seconds later, Although he'd handed control to the relief pilot, the first officer pulled back on the controls again, causing another dual input alert. The thrust levers also momentarily indicated as idle, then moved forward again, probably to try to change the situation. The captain shouted from the jump seat, "Watch out! You're pitching up!" But now it seems the relief pilot had changed his mind about the strategy, because he shouted, "I'm pitching up!" And when the captain kept warning about it, he responded that they needed to do it. "We're at 4,000 feet. The next thing that could be heard on the cockpit voice recorder was the ground proximity warning system calling, "Sink rate! Pull up!" as the aircraft fell through 2,500 feet. This made the captain also change his mind and shout, "Come on, pull!" while the first officer intervened, "Come on, pull up! Pull up! Pull up!" Both pilots pulled maximum back on their side stick, bringing the nose to 16 degrees above the horizon. The speed at this point was 107 knots forward, but an equally heartbreaking 107 knots downward. At 02:14:22, the first officer again pressed and held his takeover control button. This locked out the relief pilot's control. The synthetic cockpit voice recorder called "Priority right." The first officer now pulled back in panic and shouted, "We're going to crash," followed by, "This can't be true," and "Fompa. What's happening?" The captain ordered a 10-degree nose-up pitch, ignoring the stall and ground proximity warnings. The relief pilot tried to pitch forward one last time, but since the first officer was holding the control button, his actions had no effect. Even if he could have, it was too late to do anything about the situation. At down 02:14:28, the Airbus A330 crashed into the Atlantic Ocean at a 45-degree angle and a vertical speed of 10,900 feet per minute. The forces on the aircraft structure were equivalent to someone falling from the 46th floor directly to the ground. It immediately shattered the aircraft into thousands of pieces, and all 228 people on board died instantly. Completely oblivious to the horrible fate of the aircraft, the 4 control centers that were supposed to be in contact with the flight soon began contacting each other to verify if anyone had heard anything from the aircraft. It soon became clear there'd been no signal from the flight since 01:35, and the crew hadn't checked in at the various checkpoints where they should have. At first, no one gave it much importance since problems with HF radio contact were common in this region of the Atlantic. Various calls continued to be made between the different air traffic control centers, verifying if anything had been heard, and other aircraft flying the same route were asked to try to contact the flight, but without success. The same happened when trying to contact them via SATCOM, a type of satellite phone, including messages from the airline's notification and communication system sent from Air France. 3 hours after the accident, the flight was first recorded as missing, and 3 hours later, the first emergency message was sent from Madrid in Spain and also from Senegal's air traffic control centers. This caused the first search and rescue aircraft to be sent toward the aircraft's last known location. On June 2, 2009, 2 days after the accident, the first floating debris was sighted on the ocean surface, and 3 days later, the first debris and victims were recovered at sea. This was the beginning of a 2-year search and recovery effort that included mapping all the underwater terrain where the aircraft was believed to have crashed. The search was divided into several campaigns, with the last beginning in March 2011. And on April 2 of that year, the wreckage was finally located in a relatively flat area on the seabed at a depth of approximately 12,800 feet and 6.5 miles from its last position, transmitted by the airline's notification and communication system. This allowed the recovery of thousands of pieces, including the cockpit voice recorder and flight data recorder, which were surprisingly in good condition. The fact that both recorders were found was what finally led to the final report and the details I just told you. So what were the conclusions of the final report? Why did this horrible accident really happen? Well, the fact was that no aircraft component actually failed, but the pitot tubes and their heating elements were temporarily overwhelmed by external factors that were probably outside what they'd been certified for. This then led to a loss of reliable airspeed. And that in turn caused a cascade of temporary system degradations, warnings, and autopilot disconnections that caused great alarm to the operating crew. The crew was expected to apply the procedure for unreliable airspeed, but they never did. On the other hand, the initial pitch-up reaction by the pilot flying created a steadily worsening energy situation, discovered late by the pilot monitoring. Subsequent corrections were too small, leading to the aircraft leaving the flight performance envelope and entering a sustained stall. This fact was not understood by the pilot, very probably due to lack of training, but possibly also because they might have thought the warning was erroneous since it didn't match their mental model of what was happening. In any case, the pilots never discussed or verbalized the stall conditions during the entire sequence. The lack of identification of that stall meant the crew never initiated any countermeasures against it. This accident shocked the aviation industry and led to several safety recommendations, including a formal training module on upset prevention and recovery techniques for all pilots. That included the effects of flying at high altitude and stall recoveries. It also introduced new memory items for unreliable airspeed flights that focus on disconnecting the automatics, establishing appropriate pitch angle and power to keep the aircraft flying safely before troubleshooting. The investigation recommended installing a camera in the cockpit to show instrument indications, as well as several recommendations about pitot probes, black boxes, Airbus's stall warning system, and improvements to search and rescue. Many recommendations were made, but the most important lesson for pilots is that we really need to understand the aircraft we're flying. This means understanding all the systems, what happens if they degrade, and how the aircraft would react differently when flying at high altitude versus low altitude. And finally, never forget to keep flying the airplane. In case of alarm, stay safe by controlling pitch angle and power. Keep the aircraft flying, and only after that try to figure out what's really happened. As long as the aircraft is flying, there'll be plenty of time to troubleshoot. Look, my friend, this story was based on the final accident report, but due to its complexity and the many human factors involved, I've also used several alternative sources. I want to especially mention Understanding Air France 447 TARS by Bill Palmer, which was fundamental in expanding my understanding of the Airbus 330 system. I highly recommend it. If you enjoyed today's episode, hit that subscribe button and consider joining my incredible Patreon team or checking out some of our merchandise. This is Captain Peter Mercer. Thanks for being my co-pilot. See you on the next flight.